Hey everyone, Rohan this side, and once again I welcome you all to the YouTube Academy project series that has been started by Spartificial. And one thing that is really very exciting, and if you don't know about this project series, is for all the videos regarding the projects that we are uploading in the series, at the end of each and every project, we are having some task for you to solve. So in this particular case, we are having these two different tasks for you, and only if you are able to complete this, you are going to stand a chance to earn a certificate just by completing it. Remember this, we are not going to focus on how effectively you are or how efficiently you are coding it in order to complete this task. The main thing is if you are having the skill set in order to complete this task or not, then based on this task that you have completed or how you have completed, you will be getting the certificate of the skills that you have developed by doing this task or by going through this whole project. So that's the basic idea that we are implementing in this particular YouTube Academy project series that we have started. So do stay with us by the end of this video to know more about how you can submit your task and how are you going to receive it and how are you going to check everything. I'll be just letting you know by the end of this video. So with that being said, let us begin with our project. That is, we are going to go ahead and detect the different species of the fishes that we are having in our dataset. So I'll let you know the dataset very soon. But yes, the main task that we're going to do is the image classification task based on the different species of the fishes that are available in our dataset. So we are going to use deep learning techniques for this particular method, and that's why the name basically suggests that we are going to go ahead and do fish species detection and recognition using deep learning methods. And this project ID and the project name, again, will be using it while submitting the form. And don't worry again about this, I'll let you know everything, how you can submit your task and how you can get your chance to earn the certificate. So now let's just understand the workflow of this overall notebook. We'll be starting with the introduction of the problem, then understanding the data set on which we're going to work on this whole project, and then import the necessary libraries that we'll be using throughout this project, then do some kind of exploratory analysis based on the data set that we are having, and then the image generation and the pre-processing. Like, this is basically the transfer learning, a new technique that we'll be using in this particular project. We have never used this technique till now in any kind of projects that we have uploaded. So this is a new technique that we are going to look into, and I'll be explaining that to you as that particular task comes. But after that, we're going to go ahead and build the model and do the evaluation part. And at the end, there are some tasks for you, as I had mentioned. So these are all the kind of stuff that we are going to follow in this whole project. And let's start with the introduction to the problem. So, estimating the relative abundance of fish species in their habitats on a regular basis and keeping an eye on population fluctuations are a crucial task for marine scientists and conservationists. Diverse automatic computer based fish sample methods have been demonstrated in underwater photos and videos as alternatives to time consuming hand sampling. There isn't, however, a perfect method for automatically detecting fish and classifying their species. This is mostly due to the difficulties in producing clear underwater images and videos, which include environmental fluctuations in lighting, fish camouflage, dynamic backdrops, murky water, low resolution, shape deformations of moving fish, and tiny variances between some fish species. And hence, our main task is to get a dataset in which we are able to identify the fish species, or else we are able to classify different kind of fish species. So for that, what we're going to do is we're going to use this particular dataset. I can just go ahead and copy this, and obviously you can go ahead and read all the kind of information given about the dataset. But I'll just copy this link and I'll click on this arrow over here, and there is the option of adding the data, and I'll just search for this, and I'll just click on this plus symbol, and it will automatically be added to my notebook. And this is the data set that we are talking about. So this data set contains 9 different seafood types. Basically, there are different kind of fish basically, and we are calling them seafood types. And this includes, there are basically 9 different classes as we have mentioned. So you can go ahead and read about these names because I won't be able to pronounce it properly. So there are this 9 different fishes, and for each particular class, we are having 1,000 augmented images and their pairwise augmented ground truths. So if I just show you this very quickly, we'll be looking into this now and then. So over here inside this fish dataset, we'll be having multiple amount of, we are having black sea sprat, then gilt head, bream, house, mark, all the kind of thing. Basically, what has been written over here. We are just having this 2 different folders. One is the one that is containing the normal images of the fishes, and the second one is the ground truth of it. So That's exactly what has been mentioned over here, that for each of the classes there are 1,000 augmented images, and obviously we'll be going ahead and doing more augmentation. That's as it's one of the tasks for you, because the images that we are having in this data set is like, for the training part only 5,000 is what we are having. So it's really recommended that you can go ahead and try to do more of the augmentations, so use some more augmentation techniques and generate more of this data set. And what is the reason behind that, I'll explain all that thing while I'm going ahead in this project. So we are having this 1,000 augmented images and their pairwise augmented ground truths, and each class can be found in the fish dataset, and we have already seen all this kind of stuff. And for example, yes, we already seen this thing, so it's completely fine. And for this purpose of analysis, we shall only be using the augmented images. We won't be using the ground truth because we are not performing any image segmentation task. And I'll be telling about this thing now and then while explaining throughout this particular project. And the credits given to this dataset is nothing but what we had seen over here. It's the same guy that has been mentioned over there. And now let's just go ahead and import necessary libraries and the modules that we'll be using throughout this notebook. How are we going to use it, or why are we using it? I'll explain that as that particular part comes. But yes, what are we using it is what I'm going to explain it over here. So for the data handling part, the way the data is given to us for this particular project, we are going to use NumPy, Pandas, and the OS. And for the visualization part, as usual, we are going to use Matplotlib and Seaborn. For the data building part, or I should say the model building part, or like how we manipulate the layers of a model, how we build the layers of a model, we are going to take the help of the Keras and TensorFlow. And the layers that I was talking about we'll be needing for this particular project is the dense layers, sequential model. The optimizer that we're going to use for this project is Adam, and for the train test bed we are using the sklearn library, and we just using the model selection and importing train test bed from it. So these are the pretty much usual things that you must have seen till now. And this is the part which is something new. As I mentioned earlier, that we are going to show you the power of transfer learning. And this particular project is really a good data set that we are having to show you the actual power of transfer learning. And you can implement it in varieties of ways. And this is just one of the ways that I'm going to implement it. But yes, I'll explain a bit more about this when this particular part comes, that how are we using it, what's the meaning of transfer learning, and all that thing will just come later on. But yes, this is something new that you are looking into. We are going to import MobileNet V2 from the TensorFlow.keras.applications. And then in order to pre-process the data of the input before passing it to the model, we are using this particular two things. That is, from the MobileNet V2, we are going to import the pre-process input, and then from keras.preprocessing.image, we are importing the image data generated to generate the images basically for the data, or basically for the input of the model, as I mentioned, right? So that's the part that we are going to do over here, that's related to transfer learning or the model building part before we implement our data into the model. And then as we are dealing with the classification data set, so we are importing the regular matrix, that is the classification report, confusion matrix, and the accuracy score. Again, you must know that accuracy score is really dependent on the type of the data set that we are having. Is it imbalanced or balanced? If it's imbalanced, then I guess by now you must be very much sure that we cannot use accuracy score if the data set is imbalanced. We can only use it if the data set is pretty much balanced. Like for each class, we are almost having similar amount of samples that we are training our model for. So let's see what's going to be the case in our particular data set. But yeah, these are the basic performance analysis matrix that we're going to use. And then this is something that is I personally like to do, because Kaggle is really going to throw some kind of warnings regarding, like, the versions that we are using for this particular notebook of Pandas, TensorFlow, Keras. And so to avoid this kind of red output screen basically in each code cell that we're going to run. So just to ignore all that kind of stuff, I am importing warnings and just filtering out and then just saying that just ignore them. So these are the basic ones that we are going to use. As I mentioned, the only new thing is this transfer learning part, and I'll explain that very quickly when that particular part comes. So this is about importing the necessary libraries and the modules. And now let's move on to the exploratory analysis part. But before I go ahead and explain you, like, what is the kind of exploratory analysis that we are performing, what's the reason of it, I'll first show you the way that the data set is given to us in this particular project. Because once we get the idea of the arrangement of, like, where exactly is our data set located in the given folders, only then you will be able to understand all these kind of steps. And obviously this is a coding part, so you can do the same thing in multiple different ways. So we are not know how you can do it very quickly or efficiently. We are just going to follow a particular technique through which you can do the respective task. Obviously, if you're having some kind of other way or better ways of doing it, it's completely fine. It's completely your choice how you code it. But yes, this is what we're going to follow for this particular notebook. But as I mentioned, before I go ahead and explain what we have done or why we have done something, I'll first of all go ahead and show you the data set, the way that the data set is given to us. So over here, this is the main thing that in which we are having our data set. So in this, there is a folder of the fish dataset. That's the folder that is required for our particular data. And if you click on it, again, you will be able to see this one more folder inside it. It's the same name, fish underscore dataset. And now if I click this, you will be able to see all the different kind of classes of the fish that we are having. So I guess we are having 9 different classes, Black Sea, this guilt and all the kind of names. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we are having 9 different categories over here, and inside these categories we are having 2 different images. One is for the images and one is for the ground truth. Basically, these are the images of that respective image that we are having in the original image, and we are just segmenting it and creating the ground truth out of it. So but as I mentioned, we won't be using the ground truth. We are not dealing with the segmentation part. We are only dealing with the classification part. So we can ignore this, all the classes that we are having. We can ignore this GT files. If I just show you, even in the second class we are having a folder for the segmentation part, and one is just for the normal images. And yeah, it will be the same for all the kind of different classes. If you want, you can check individually, but yeah, that's the basic idea that we are having. And the main idea, the main images that we're going to use for the training part is nothing but from the first folder, which does not involve the name GT, and all the images that are present inside that. That's our main images, and these are the images that we need to fetch and feed it into our model so that we can use it for the training part. So yes, this is the way through which our data set is given to us. And now let us move ahead and focus on the coding part. So in this first coding cell, what we are trying to do over here is we are trying to grab the name of different classes, or you can say different species of fish that is available to us in this particular data set. So how are you going to do it? So for that, I'll again show you the data set. So as we can notice, all the kind of different classes are present in names of the directory over here. So what we are going to do over here is we are going to create a master directory. It's nothing but this particular path. So I'm just going to copy this path and paste it over here. So that's what is already done. And I'm saving it in the variable named as dir. So because I know that, like, all the material or all the kind of data set or all the images are present after this particular directory. And that's the reason we are creating this particular directory as the master directory. And then we can access all the kind of different folders or the directories that are present inside the same directory. So after doing this, my main task is to grab the name of the folders over here, or name of the files, or name of the directories that is present over here. So what I am going to do for that is, if you can notice, inside the same directory we are having this 9 different folders, but along with that we are also having 3 files which is having the dot extension, right? So there is a dot present in the name over here, over here, and over here. So the main thing that we are trying to do over here is I'm going to loop through this particular directory, and if the directory name is containing dot inside it, I am going to discard that. I'm not going to do anything with that. But if dot is not present, only and only if dot is not present, I am going to take it as the name of the class and store it inside this classes list. And how are you going to do this? I'm going to create the list comprehension, and in the list comprehension I am saying for I in os.list directory of this directory. So we are going into this path. We are looping across the names of these different files that we are having inside this directory. And if dot is not present in I, if dot is not present in the name of the files that we are having, only then grab it and store it inside this particular list. So that's what we are doing, and that's how we can get the output of this 9 different classes that, as I mentioned, is nothing but the names of these different folders that we are having. So yeah, that's what we are doing in the first particular coding cell. Then moving on to the next coding cell. And over here, what we are trying to do is we are trying to create a data frame like this, which basically is going to contain 2 different columns. One is for the path and one is for the label. So this path is nothing but the path of all the different kind of images that are present in the respective classes. And these classes are nothing but the labels, right? So we are going to say that, okay, if we are taking, because we are seeing the example of house Mackerel over here, whatever is the pronunciation. But yes, as we are looking into that particular name, what I am doing over here is I am going to open this directory. So inside this directory, again, we are having 2 different directories. One is the ground truth one. As I explained, we don't really need this for the classification purpose. We can use it for the segmentation purpose, but we can completely ignore this for our particular project. So we don't want any kind of directories that has a GT inside it. But now if I just open this folder, so in this folder, all these kind of images. So if I just copy this path, so this path that I've copied is nothing but the path that is present over here. So it goes across this particular folder, then this folder, then comes across, like, it loops across this whole directories that we are having. And then whenever it contains this house Mackerel folder, it takes all the kind of paths inside it, and one by one it stores inside this particular data frame. So each row is basically a different path of these images that we're going to use in the training purpose. And also respect to labels, so from which directory are this images belonging to, that respective label is going to be placed inside the second column. So that's the kind of idea that we are trying to bring using this particular code. So many of you must have noticed that, I have changed the 1 to -1 over here. The reason behind that is that you will understand, like, being a beginner, it would be very much difficult for me to explain why am I using 1 over here, why am I using -1 over here. So to keep it simple for the beginners, I would just did this particular change. It's going to give you the exact same output, even if you're having a 1 or a -1 over here. How? I'll explain that when that particular part comes. But now, as I mentioned, the main task is to create a data frame with 2 different columns. So how would we get these columns? So for that, we are creating this empty list, and inside this path list, we are just going to fetch all the kind of path of the images that we are having, that we are going to use for the training part, and its respective label. So from which class did we extract all this kind of paths? So that respective label, we are going to store it inside this label list that we are creating, or the empty label list that we are creating. We're just going to append all this kind of names of this particular directory. Right, so that's the kind of idea that we are going to go through, and for that we are going to use os.walk dir. So this dir, if you remember, this is nothing but the master directory that we have created, and os.walk, it simply is going to give us access to all the different directories that are present inside this main or the master directory, get access to all the paths of the directories present inside it. And these file names are nothing but the names of the files that are, like, directly present inside the directory. So we don't have any more subdirectories. These are the only final names of the files that we are having in the directory that we are looking into. So the directory name is nothing, as I mentioned, is the path. So for example, if the first is nothing but this fish underscore dataset directory itself. So inside this directory, what we are doing is we are having different kind of names. So now in this names, again, we are having different kind of outputs. We are having this .txt file, that .dm file, sorry, .m, not dm, .m file, then .txt file. And if I go through, let's say in this particular folder, then again we are having a subdirectory. Inside this directory, we are having these files. So these file names are nothing but all of these files that are present inside the path of this particular directory. So, and that respective directory is going to be getting, like, we are going to get the access with the help of this particular dir name variable. All right. So I hope it is clear. I'll quickly give you a revision over here. So this dir name is nothing but the path of the directory inside which all the file names that we are going to go through are present. So these file names are nothing but only these file names. For example, this all the zeros 1.png, it's not the path, it's just the name of the files that are present in the directory that we are looking into. And this directory is the path, not the name, but the actual path of the directory, where is it present, and all the file names that we are going to go through, in which directory, in which path is it present. So these are the kind of details that we are going to get through this os.walk of the main or the master directory. that we have created. And then because this file names, we can see there are a lot of files present inside a particular directory. So in all these file names, we don't exactly know, like, if all the kind of all the kind of files over here is going to have .png. Like, let's say in the main folder we are having this .txt. What if we are having this kind of .txt or some different extension than png? Our main task is to fetch all the files that are having the name or the extension as .png, because these are the images that we're going to use for the training purpose. And so see, that's what I'm trying to do over here. The file name that we are having is nothing but these are the names of the files, as I mentioned, right? So these are the kind of the names of the files. And if we are going to use os.path.split text, so if I'm using os.path split text on this particular name of the files, it basically splits the root. Root is basically everything apart from this extension. So .png is a separate entity, and everything before that is a separate entity. So now we are having two different elements. So in order to grab the element that is a .png, so if you can notice, the first element is nothing but the IDs of the names or whatever you want to call of that respective image, and the second entity is the extension version. So in order to grab this second element in Python, we know that the indexing starts from 0 and then it goes to 1. So in order to grab the second element, the index that we are going to use is 1. But now if you notice, there is also a different way of indexing in Python. We are having this ability to use negative indexing. So negative 1 basically represents the last element that we want to access. So the last element is nothing but the second element. So even if you use 1 or a -1 over here, it's still going to work, right? So that's the reason that I changed this thing. But again, for the beginners, to keep it very simple so that I don't again have to explain why have I used -1 over here. So to keep the thing simple, I'm just I had changed that 1 to -1. So I hope that part is pretty much clear to all of you. And yeah, so now what we are doing is, inside all the file name, if and only if we are having the .png extension, then and then we can go ahead and do this particular steps. So what is the steps? So if the directory name, again we are using the the path of the directory, and we are splitting the path of the directory. So if I just copy this particular, let's say, directory, and let's say I'm just pasting it over here in the markdown cell very quickly. So yeah, this is the kind of the directory we are present in. And if you could notice, there is no GT over here. We don't have anything like space GT. All right. So this GT, how did I get this GT? If I just close this particular thing, we are having this GT folder as well, right? So out of this two directory, how do we know in which directory we are present? So for that particular step, we are doing this particular coding. If the path and this dot split basically splits the whole path in a way like it will create a list, and inside that list, if we are having a spaces in between, it will just create different elements of this strings basically. So all this kind of spaces in between will be removed. It will be just all kind of path will be split into different elements. So this will be your first element because there is no space in between. This is your second element. This is your this particular thing will be your third element. This is your fourth, fifth, and sixth, or in indexing in Python, if you can say, this is the last element in the list. So again, we can grab it with the -1. So if the last term or if the last element in the list is not GT, only then I'll allow my this coding to go further. Else I'll just not go ahead in that particular directory, because as I mentioned, this JT are the files that we don't need. It's only for the segmentation purpose, or that particular stuff, not for the classification part basically. So uh, if the file name, inside all the file names that we are having, all the file names, if first of all it is a .png, only then go ahead. And if this file names, if the file names that I'm looking for and its respective directory is not containing GT at the end, only then we are allowed to store the name of this directory inside this label list that we have created, and all the file names over here inside that directory, we can concatenate this directory which each and every file, so that we can create a list of the paths, and then we can just go ahead and create a data frame out of it. So how can we do it? So as I mentioned, I'll just go through it very quickly so that it's a quick revision for you as well. So for all the kind of directories that are present inside this fish dataset, and inside all the directories, the file names that we are having, if it is containing this .png extension, the respective name of the folder, the respective name of the folder. If it does not contain GT, we are going to take only that directory, and that directory I'm going to use the name of this directory and store it inside this label. So let's understand how we can store this particular names of the directories which contains this PNG files, but the folder or the directory name is not containing GT inside it. So how are we going to do this? So let's say that we are having the name of the or the path of the directory like this. So I'm just going to remove GT because we don't really need it. And now I'm going to use os.path.split on this particular path. Now this is a bit different than this os.path.split text. Over here we are trying to split what is the extension and the previous part apart from the extension. But over here what we are doing is we are trying to separate all the other part apart from the name of the directory and the name of the directory itself. So we are going to create a list of two elements, and because the second element is either on the first index or the negative one index, that's exactly the same thing that we had done over here. We can use 1 instead of -1 over here, and similarly -1 instead of 1 over here. It's completely fine because in this particular use case, the -1 and 1 is representing the exact same element inside the list. So in order to grab the second element, that is nothing but the name of that particular directory, we are using os.path.split, and this negative one is going to grab this second element, and that's what we're appending it in the label. Now it's going to walk through each and every directories, and if the directory is containing the PNG file and if its respective name is not containing GT at the end, we are going to store all of these names of these classes inside this label list. And similarly what we are doing after that is we are appending all the kind of directories like that. We are using this the whole path of the directory. So let's say if this is the particular directory which is not containing GT at the end, I'm using this as the first part over here, and the respective file names I'm just looping across every file name, right, in the file names that is present. So for each and every file name, I am concatenating this directory with its respective file inside it, so that we are containing that's the reason we are able to get this different paths for that same label. And that's exactly how we are going to do it. This dot join is basically joining two different strings. This directory is nothing but this copied path of all these folders which is not containing GT at the end, and all the files inside it will automatically be getting concatenated because of the for loop that we are using. So once this for loop is completed, once we are done completing our walk across the whole directories that we are having inside this master directory, we will be able to get one list that is fully containing the labels, and the paths are nothing but the respective files that are present for the respective labels. So that's the kind of thing that we have done. Now let's talk about how we can create the data frame. So for that we are going to use pandas, and we have already imported it earlier as a PD. So that's why we are using pandas.data frame, and the name of the columns that we are giving over here is the first name is the path and the label, as you can already see it over here. Now what is the content that we are going to pass inside this path column? What does each and every row of the path column contains? So it's nothing but the respective values of the path list that we have created. It's the same exact paths of the images that we're going to use for the training part. So that's what we are passing it inside this path column. And similarly for the label column, whatever is the respective label that we have generated for that respective path, we are going to import it over here in this particular fashion. And that's the kind of the data set that we'll be having. I'll just quickly delete this part so that it's not going to be a disturbance when I'll be sharing this with you on GitHub. So yeah, we are done with this extensive coding. Even though it's very few lines of code, you can see the power of it. Only by this few lines of code, we are able to go through each and every directories and able to grab all the files. And then we have created a particular data set in which we can then use it. We can now go ahead and split this ahead into the training part and the testing part, and we can do all that kind of stuff. So that's the power of Python. With only few lines of coding, you are able to do this kind of thing. So yes, now just to visualize, what is the first path, what is the path that is contained in the first row. What I'm doing is I'm just to show you guys. So this df.path of 0, because we are in the label of horse McCarroll, whatever is the name, I'm not able to pronounce it properly for sure. But yeah, let me just show you where is this particular, yeah, it's over here. So inside this, we are having this particular folder. So in this first part, is basically your 929th image that is present inside this. So that's your first path present over here. Similarly, we'll be having all the different files that is present inside this with the .png extension, and the respective label is a horse Michael. All right. So I hope you all are getting the idea of what we have done so far. And if at all this part was a bit confusing for you, if you are not able to understand anything, you can please let us know in the comments, and we'll approach to you as soon as possible to solve any kind of doubts if you are having. And now let's try to get all the kind of information that is present in the data frame that we have created. So there are total of 9,000 paths and the labels that we are creating, and both of them are of the type objects. So after this, what we are trying to do is we are trying to check the value counts that is present in the data set. So what I have done over here is I'm going to go ahead and grab the labels that we have created, all the kind of labels, and I'm just going to count how many times this particular label has been repeated. So if you can notice, all the kind of classes or the labels are repeated for 1,000 times. So it basically means that this data set is pretty much balanced. For each and every class, we are having exactly same amount of data for the training part. So this is really good. We can use accuracy score over here. We don't really need to go ahead for the classification report in this particular use case. But yes, anyway, I'm going to show you the classification report, the accuracy score, and all that kind of stuff. All right, in the performance analysis part. But yes, that's what we are doing in this particular part. It's pretty much straightforward. This value counts is nothing but, like, a method of pandas, which is going to give you inside the data frame, if the column that you're looking into, what are the values that are present inside that label column, how many times has that been repeated. That's what we're going to get. So that's the output that we have got. And this is just the visualization part of, like, what we are dealing with. I'll just close this part over here so that it's look a bit cleaner. So yes, what we are doing is we are using index equal to 0, then creating the overall figure size to get this neat and clean subplot that we have created. Again, this number is not like something that comes up to me or anyone. It's just like, if the output is not looking neat, you just keep on changing this figure size until and unless you get, like, the best output for you to visualize it. So what we are doing is, for each and every label that is present inside the label column in the data frame, i'm I'm using this dot unique. This dot unique is going to give me all the labels that is present inside this column that are unique. So all the 9 different columns, we are able to fetch it. And after fetching the this names of this labels, what we are doing is we are creating a subplot of 3 by 3, because we are having 9 different categories. So we are going to plot 9 different subplots. And this index plus 1 basically means, because we are starting with 0. So because we are starting with the 0 index, this plus 1 basically means that, okay, yeah, I'm going to plot the first particular class on the first position. Then when the index value will become 1, how is it going to become 1? Because if you can see, I've used the increment operator. So once we get all this kind of index, we are basically getting where to plot a respective subplots. This is the first position, second, third, fourth, all the way up to the ninth position. So obviously, in terms of coding, you can do it in any kind of way in which you have already practiced this kind of things. But this is what I have practiced, this plus 1. If you had started this index from 1, and then if you just write idx over here instead of plus 1, because we know that this particular label are having 9 unique values, so we know that this is going to iterate for 9 different times. So automatically this index will reach by this increment operator to the value of 9. So in that case, we don't really need to use plus 1. So, but irrespective of this fact, how you code it, the main part is how to get this kind of subplot. So I hope I explained you how, what is the purpose of this idx plus 1 over here. It's just used to, like, plot different images for the respective class that we have got. All right, but now how exactly are we plotting it? How are, like, what is this particular line doing? So this is the line for the respective labels that we are seeing. So how did we get it? So it is with the help of the pandas data frame that we have created. So what we are saying over here is, in the data frame, if the label column is having that respective unique value that we are looking into. Remember, this is the for loop that we are going through. So all the 9 different unique classes that are present inside the label column, we are going to go through them one after the other. So for whatever that unique column is present, grab the location 00. Now what does this 00 mean? So for all the kind of labels that I'm getting, so all the kind of data frame in which we are getting the labels, on the 0th row and the 0th column, whatever is the path, grab that path for that respective label. So if I'm in the horse markle, this particular label, grab me the first index, that is the first row and the first column path, grab that particular thing and display it. How are you going to display it? With the help of the plt.imgrade. So whenever we are using the imgrade from matplotlib, it can convert the image path into the numpy array, and then after using plt.imshow on this numpy array, we can actually visualize how that array looks like. So we know that image is nothing but the representation of pixels that are stored inside this arrays, and then we can visualize this arrays with the help of this plt.imshow, and that's exactly what is happening. So for each and every unique class, the first path that is stored inside that respective label, we are trying to get that first path and displaying its respective images. And then to plot, like, which is the, like, which this particular path belongs to which label, I'm just using plt.title and I. Remember, I is nothing but the name of the label. You can just change this I to the, like, class or labels, just to, like, make it even more better for understanding. So I'll just do that for you, so that you can, I'll not use class, I'll just use label. So instead of I, wherever there was I am just replacing it with the value label. So this is nothing but the unique label that we are having, right? And I guess let's just write a unique label itself, so it's much more clear when you are looking into this. There are no more confusions. I must have done it earlier, but I apologize for this, but I'll just do it very quickly, and I hope I have not missed any kind of label. So yeah, over here I was replaced with unique label. Over here also unique label and unique label. So I guess we are done. So this looks good. Now in order to avoid any kind of marks on the axis of x-axis and y-axis, like, what is the length, what is the width, in order to avoid all that kind of output, I'm just using plt.axis and just turning it off. And then yes, this for loop keeps on going on, and each and every position will be getting the subplots of different unique classes, and the first path is nothing but what we are able to visualize it in the subplot. So I hope you are now able to understand what is the idea that is going on behind this plotting part. This visualization purpose is just done for us to realize what are the kind of different fishes, how does it look for the respective classes, and that's all about it. So I hope that's pretty much clear. And now we can go ahead and do the test train split. So as I had already talked about this in all the previous projects and including in this project itself, I told you that we'll be using this test train split once we are having the data that is ready for us to split. So this is the exact data frame that we are going to use in order to split it. One part will be remaining for the training, and the remaining chunk will be used for the testing part. And we can again go ahead and, create the validation data set as well from the training data set. So let's just try to do all this kind of stuff what I'm talking about. So here is where we are creating the train data frame and the test data frame with the help of this train test split that we had imported from the sklearn pre-processing part. Basically, if you remember, in the first coding cell, while we were importing all the libraries, we had imported it from that particular sklearn. So from that sklearn, we are importing this train test split. We are passing the main data frame which we want to split into training part. So how many rows are going to be allocated for the training, how many rows are going to be allocated for the testing. So that's what we are basically going to get as an output. So this is the data frame which is going to be worked upon. Like, this is the data frame that is going to be splitted into the training and the testing directory. And then comes this train size. So this main data frame that we are having, the main data frame, we are going to split it at random, and 80% of the rows inside this data frame will be passed on to the training data frame, and the testing data frame is just going to take the remaining, that is the 20% of the data. Now every time that I'm going to create this randomness of the split, that this randomness, to keep this randomness same so that we get same kind of split every time, we are fixing the random state at 42. And the shuffle equals to true, that we are first of all shuffling the data. And once the data is shuffled, if the rows inside this data frame are shuffled, after that shuffle, we are creating this 80% split at random. And every time we are going to run this code, it's going to create this randomness, the same kind of shuffling and taking part of training and splitting it into the testing as well. So that's the kind of thing that we are trying to perform in order to generate the trained data frame and the test data frame. So once we are done with that, so as we are containing 80% of the 9,000 images that we were having in the main data set, so the 80% of 9,000 is basically 7,200, and the remaining 20% is nothing but the 1,800. So the shape of this data frame for the trained DF is there are 7,200 rows with two different columns, one for the path, one for the respective label. And for the testing part, we are having 1,800 rows with again the same two columns. And now comes the image generation and pre-processing part. So now to understand how we are pre-processing the given data set that we have created above, how are we going to pre-process it? So this pre-processing basically is going to be in the exact same way of the model that we are trying to use. So obviously you must be confused over here if you are not at all aware about the idea of the transfer learning. So let me give you a very brief idea about the transfer learning over here. This is the right time that I can introduce it to you. So what happens inside the transfer learning is we are using a pre-built model that is trained on a very large data set, and the project that we are doing, the classification of the different species of the fish, we can take a very similar kind of data set on which this kind of pre-built models are trained on or built on. They this big companies like Google, Facebook are having their own networks which are trained on this large data set, and it also has very similar features as compared to what we are having in our particular data set, that is the fish. So we are trying to use this kind of networks that are trained on this large data set that are pretty much similar to what we are doing. We are trying to use the weights and the bias, basically the model parameters of that particular pre-built models, and implementing it onto our particular project. So what are the benefits of it over here? The benefit is now there is no need of thinking about how many convolution layers would be there, how many max pooling would be there, how many filters to use, what is the pool size that we have to use. All that kind of stuff is going to be taken care by the pre-built model itself. So we are using that. The reason we are calling is a pre-built model is because it's already built by someone, and a lot of people are already using it for this kind of different tasks based on the large data set on which it is getting trained. So this pre-process input is basically, if you remember, we had imported this pre-process input from the MobileNet V2 itself. So MobileNet V2 is the architecture that we are going to use that on the dataset that we are having. So in a way, we are saying that please go ahead and pre-process my images in a way that were exactly done in the MobileNet V2. So whatever was the pre-processing steps, whatever standardization, normalization, whatever it is, whatever steps were used for that particular data set, please go ahead and do it exactly in the similar way for our particular data set. And I hope you have now understood the idea about what is the process behind the transfer learning. Why do we use it? So it's just to ease our task in order to choose the different layers or different filters and all that kind of stuff. We are going to get rid of it. We are going to use a pre-built model that is tested by huge companies, and the way that they are going to pre-process the inputs, we are going to do that exactly the same thing over here, and just create train generator and the test generator. But I'll give you a quick demonstration of MobileNet V2 in a while that once we are going to implement it. But for now, we are just creating the generator that we are going to pass it into the MobileNet V2 architecture. But yeah, these are just the generators that we are creating. And now in order to get images out of this generator, we are going to do one more step. That is this particular part. We are going to use flow from data frame. And now let's just try to understand what is this flow from data frame doing. So let me just go through all the kind of input arguments, and then I'll be able to explain what this is exactly doing. So for the training images and the validation images, just remember that we are going to use this train generator because we are creating the split over here such that the 20% of this training data is going to be used for the validation part, and the remaining 80% of it out of that 7,200, all right, out of that particular one, 80% of that value will be used for the training part. So then that's the reason why we are using training images and validation images. We are creating these two different things now out of this one single split that we had created for the train generator. All right. So in the training part and the validation part, we are using the train generator, and respectively the data frame that we are passing is obviously of the training part. So you can see this train data frame and the train data frame as the input for the first two train images and the validation images respectively. And the last one is the testing part. And that's why we are going to use the test generator, and the respective data frame would be the test df. But now everything after this is almost going to take the similar kind of input. So let me go ahead and explain that part. So in all of these data frames, what is the first column or the x column representing, and the second column or the y column is representing? So x column is nothing but the images or the path of the images that you are going to provide. In terms of the data frame, we always provide the path and will automatically convert it into the images as we had seen earlier. And the y column is nothing but its respective target. The target is nothing but the name of the classes or name of the labels basically. And now we are resizing that original image, whatever was the original shape of that image, we are just resizing it to 224 by 224. And the color mode is RGB. So it basically means we are having three different channels of that particular image. And this class mode equals to categorical. It basically means that all the classes or all the targets that I am having, I am converting it to a one hot encoding format. So all the labels from these names are now going to be converted into the one hot encoding labels. Now, what is the one hot encoding labels? See, machines are not basically going to use this text in order to understand, like, what is going on. It basically understands the numbers. So we are trying to convert all of this text of classes into numbers. How are we doing it? With the help of one hot encoding. Don't get confused with this. This is not the one hot encoding. This class mode is just going to give us what is the index of each of this class. So because we are having 9 different classes, the respective index is given to us as for the Black Sea Sprat, it's 0. Then the next one is 1 all the way up to 8. So now in order to visualize this one hot encoding, let me just go ahead and show you this particular part. So on the second index, it's 1, all the under index are 0. Similarly, over here, the first index is 1, all the other indexes are 0. So what does it mean? It simply means wherever there is 1, it's the respective class that is being denoted over here. So the second class was this guild or jilt, head, brim, whatever we pronounce it. But yeah, just like me, see, machines are even not able to understand this particular text. So that's why we are just converting it into the numerical format basically. I hope you are getting it. This is the way through which we are converting or making our model or our computer or our machine understand what is the class of the image that is being fed as an input to the model. And then respectively, it's going to learn all these kind of things, all the features from these images. It's going to grab all these kind of features and grab the specific uh, peculiarity out of it, and then it will learn that okay, yeah, if these are the kind of features present inside that image, then it belongs to this particular class. If these are the features, then it's this class. So we are going to provide 1,000 of inputs, not 1,000 actually, because we have now splitted it into, first of all, the 80% split for the training part. Then again that 80% was split into another 80% for the training part and 20% for the validation part. So again, we are not providing the 1,000 images for the training part. But yes, obviously, as an exercise, you can go ahead and augment this data to create much more of the training data set, so that you are not going to face any kind of issues because of the overfitting and that kind of stuff. But anyway, that's the later part of the discussion. But let me go ahead and come back to this particular input labels or the input arguments that we were having for the flow from data frame. So I hope everything is clear till now. That we have created this labels into its categorical format. That is, we have converted it into the one hot encoding format. And then the batch size. See, the main idea of this flow from data frame is to generate different batches of a particular size of images. So this batch size of 32 basically represents that in each batch that I'll be passing to the model, it will contain 32 images. So which 32 images? It's completely at random. And that's why we are also shuffling the data. How is it going to shuffle? In exactly the same way, we are going to use the random state or the random seed value as 42. You can obviously choose any other way of splitting the data set, but the way that we are choosing is the random seed of 42. So every time again we are going to run this code, it will be giving us the same exact shuffle. It's completely random, but all this kind of randomness is always going to repeat once we just rerun this code. So that's the beauty of this shuffle equals to true, and then just assign a random seed to it. So that's what we are doing it for the training part and the validation part. Now for the testing part, we don't really require we don't really need to shuffle this kind of images, because these are the images that we're going to use, and see what are the kind of outputs that we are getting. Is our model able to identify by a given image if it's belonging to this class or that class? That's what we want. So that's why we are not really bothered about, like, shuffling the data over here. But even if you do it over here, it's completely fine. However, it's not going to matter. So just to save the computational power, we are not doing that particular step. But yes, after the seed, we are having one more input argument, that is subset. What does it mean? The subset of training and validation basically refers to the split that we had created in the training generator. So this training generator, or the train underscore generator, 80% of the data is going to be used for the training part, and that's why this subset equal to training is representing that 80% of this data from the train generator, and the remaining 20% is going to be used as the subset of the validation. So that 20% is going to be used to create this validation images, and the remaining 80% is going to be used for this training images. So that's the kind of thing that that's how we are using the flow from data frame in order to, like, use these generators and create respective images out of it. And again, I'm going to, like, show you the proper way, like, what exactly has been happened out of this outputs that we have got. But yes, I hope you understood the basic idea of what is the flow from data frame. And time after time, I'll help you realize the power of Python in this kind of projects. Because just imagine, in order to explain this one flow from data frame, it took me about 5 to 6 minutes for me to explain it to you. And only this one line of code is doing all these things for us. So it avoids all the kind of hustle that we used to do previously, where we used to, like, do all the kind of stuff coded manually by ourselves. So that's the power of Python. Now, with the help of, like, Keras API, we are just using one line of code to do all this kind of stuff for us. So I hope you are understanding the power of Python when it comes down to this kind of projects. But anyway, let's just go ahead and try to understand the kind of the outputs that we have got out after running this particular cell. So this training images, validation images, and the testing images, it's just showing that all of them are having 9 different classes. There are 9 different classes, and for each of these classes that we are having, for the training images, we are having 5760 images. For the validation, we are having 1440 images. And for the testing, it's 1800 images. But now you must be wondering, right, that we had 7200 kind of images for the training part. So what are these kind of numbers? So it is nothing but, if you remember, we had created the split in the train generator. So out of that 7200 images in the training, we again created a split of 80-20. So the 80% of 7200 is basically 5760. That's going to be used for the training part. And the remaining part out of that, if I just subtract this value from 7200, I'll be left with 1440. So these are the images that will be used for the validation part. And this testing images are not changing at all. It was again 1800 before, and it's still 1800 now, because we did not perform any kind of split over here. It's just as it is. We did not do any kind of changes over here. So that's the reason we are getting this kind of output after running this particular cell. And let's go ahead. And now over here, this particular coding cell is helping us visualize the classes that we have created. What are the indices that we are giving to it? So this particular class is having the index of 0. This label is having the class of 1. Similarly, 2, 3, 4, all the way up to 8. I've already explained this part, so I'll just go over it very quickly. We are just trying to ensure all of the images or all of the training, validation, and testing images are having respectively same indices. Because if it's not same, then the model will just learn it in an incorrect way. So we are just ensuring that if all these three are having the same kind of labels assigned to that respective targets. All right, so that's the kind of thing. And now we are going to display this. We have already again seen this as well. For the respective images, for all the respective labels or the indices we are having over here, our model is able to understand, okay, this is your first class, this is your second class. It is not really trying to think about in terms of text, it's trying to think about in terms of numbers. So now we can again do one small pre-processing step in order to visualize the outputs. If this is belonging to the second class, what is the title of it? Is it this title? Is it this title? We can do all that kind of stuff. But because I really wanted you to realize what a one hot encoding is, that's why we are using the labels over here like this, so that I can help you understand it. But obviously, as I mentioned, you can do just one more line of coding and just display the text of the respective this is just a dictionary, so you can this is a key value pair. So you can just describe the key of the class indices, and that just one line of coding can be represented or just convert this one hot encoding into its respective label. So that's what you can do. But again, that's not at all useful because we already done it over here. We already visualized that. So that was the main purpose for you to understand how the targets have been changed from a text to a one hot encoding format. And that's exactly how our model is going to learn the this in a supervised learning fashion, that we are having an image and we are telling them, okay, if these are the kind of features in it, then this is the kind of label that we are giving it to that image, respectively for all the images that we are using it for the training part. And now we are going to use the training part and provide this thing to the validation part as well. Like we are trying to see in validation as well, if this kind of training was done successfully, and if it was done successfully, what is the kind of outputs you are getting for the validation part. And similarly for the testing, if validation is also performing well, how is it performing on a completely unseen data where we did not use any kind of split in between. It's just that we are having a different set of images that we have not yet passed into image in any way. So I hope you have understood all the idea till now. And now comes the part where we are going to build the model from the pre-built model. Obviously, the pre-built model, as I told you, it is built on a huge data set. So because it's a huge data set, it will have multiple classes, not just nine classes, right? So in order to just change the top layers of this kind of pre-built models, I'm going to make use of the dense layers and the optimize and all that kind of stuff. I'm going to use it right over here. So I'm going to create or manipulate some kind of layers of the pre-built model, and then we're going to evaluate the output of this particular model. So that's what we're going to use. So what happens in this mobile net v2 architecture is something like this. It can be used for the classification part, it can be used for the detection, it can also be used for the image segmentation part. But now the reason that we are using it over here is for the classification part. And the block of mobile net v2 is in the way that, like, we are having a bottleneck input, then a convolution is happening of filter one by one with the ReLU as an activation function over there. And then we are doing a depth-wise convolution with the filter of 3 cross 3. Then again, we are having the ReLU as an input. So this is the kind of, this is kind of the building block of each and every block that we are using in the mobile net v2. And we are having multiple of such layers, and we are trying to create the output with respect to this. So we'll able to understand much more better about this while we'll be looking into the model summary. And then you'll be able to see convolution layer, then the depth-wise convolution, then again a convolution layer, and you'll be getting some kind of an output. Then again, it will be used to create this kind of outputs really from this inputs, and all that kind of stuff we'll be able to see in the summary part. So you can just go ahead and read this particular thing by yourself when this notebook will be available to you. But now let's just go ahead and import our pre-trained model, that is the MobileNet v2. So how are you going to do it? Again, we have imported MobileNet v2 separately, so you can just ignore this kind of stuff. But yes, it's completely fine even if you are not doing it. So for the pre-trained model, we are using this MobileNet v2. And the input shape, we know that the input shape that we have created is of 224 by 224. And remember, MobileNet v2 needs at least 32 by 32 as the size of the input image. But now, because obviously we are way more away from the 32 by 32, it's completely fine. So in the pre-processing step, we had resized our images into 224 by 224 with 3 different channels. And that's the reason that we are passing the input shape to this MobileNet v2 of our images as 224 by 224 by 3. Now this include equals to top basically means the classification layer. Do you really want to include the classification layer? No, we don't want to do that, because now our classes are only 9. This MobileNet v2 are having multiple different classes, and that's the reason that we are not including the last layer or the top layer. That's what we call it in terms of machine learning, the top layer, basically the last layer that we are having for the classification purpose. And the weights, see, the ImageNet is the data set on which this MobileNet v2 is trained. So the weights that we are importing of the MobileNet v2 architecture is of the ImageNet data set. And now that we can see that the next thing that we are remaining is with the pooling. Like, what does this pooling basically mean? This pooling, like if we are just dealing with any kind of a classification task, what basically happens is we have multiple convolutions going on, pooling going on. But at the end, before we go ahead and say that, okay, we are getting all the kind of features, we got the information from all the features present inside this data set. Now, out of all these features, if we are feeding it to our model as an output, how are we doing it? we usually convert it, whatever is the dimension of that output image, we convert it into a one dimensional array. It's just going to work like in, like, an input array of any kind of a neural network, right? So that's kind of stuff we are doing. We're trying to convert all of this 2D or 3D kind of images that we are having into an only a one dimensional column that is going to pass through last few layers of the model, or you can directly pass it to the output of the classification layer itself. It's completely up to you how many dense layers do you want to add, or the hidden layers do you want to add after flattening this particular image. So now, how are we exactly flattening it? Is it just the normal flattening that 2D becomes a one dimensional column, or in some kind of a different fashion we are doing it? Are we still taking, are, like, what I'm trying to say is, are we still focusing on some more important features present in that 2D or the 3D image, or whatever is the shape of that image? If yes, the best way we basically do in this kind of classification task is, we either use global max pulling 2D layer, or global average pulling 2D layer. So average is basically based on the pool size that we are choosing. It's going to scan across all the kind of image that we are having, and after all this kind of pooling filters that we are implementing, what is the average of all the pixels inside that pooling layer that we are choosing? It will take the average and represent it on the first index of that column that you are trying to create, the one dimensional column that you are trying to create. That kind of stuff basically happens. That's a very overview of, what is the idea of the global average pooling. It's just used in a way to generate that one dimensional column out of that n dimensional image output that we were having in the previous layer. So that's a very pretty much an idea that we are, in order to flatten the whole image into one dimensional, we are just taking much more prominent features from that last image, and then still we are passing that as in one dimensional input, and then we are passing it ahead to the dense layers before we reach to the final classification layer. That's the kind of thing that is happening. So yeah, that's what we are doing in the pre-trained model. So from the pre-trained model, we are using all this kind of stuff. And do you want to train this model that we have created over here? The answer is no. Again, because we are using this pre-trained model, so why would we train it again? So that's the reason we are using trainable equal to false over here. And then we are moving ahead. And after, after this global pooling layer, basically the global average pooling layer, how do I want to continue after that? And the layers that we are adding after the global average 2D pooling layer basically is the two dense layers and the final classification layer with the 9 different outputs. And that's the reason, because it's a multi-class classification, the activation that we are using is softmax and not the sigmoid, because sigmoid is basically used in the binary classification when we are only having only two classes, either this or that. But over here we are having multi-class classification, so we need the probabilities for each and every output, and the probability that will be the highest out of the 9 will be the one that will be considered as an output. That's the kind of stuff that goes on in this last layer. But before that, so what we are doing over here is, in the pre-trained model, we are grabbing the inputs of the pre-trained model over here to basically create a final model, right? To create a final model, these are just layers that we are creating. We still have not created the final model. So in order to create the final model, we are grabbing these inputs of the pre-trained model. And after this, actually, in the starting part, I said that we are going to use the sequential API of building the model. But over here, actually, we are using the functional API. So what we are doing over here is, we are using we are actually using this pre-trained model. The outputs of the pre-trained model is nothing but all the layers till the global average pooling 2D layer. All these kind of layers are stored inside this particular pre-trained model output. So in order to add the more layers after this, so we are using this functional API to do that particular part. So after this global average pooling 2D layer, I'm adding this dense layer with this activation of ReLU. Similarly, the same kind of layer. But now if you can see, the input over here is the previous layer. Over here also, this is nothing but the previous layer's output, basically. That is the output of the pre-trained model. So that's the kind of stuff that is going on. And over here, that's the last layer, the classification layer, right? So that's what is the outputs layer, or the output layer basically. So that's where we are creating our model from the inputs till the outputs. This is the first layer that we are having. This is the last layer that we are having. And everything in between that is going to create our whole model that is going to be used for our particular use case of 9 different classes. And now in order to print this model summary, we are using model.summary. And then to compile, we are using the optimizer Adam. The loss function that we are using is categorical cross entropy, and the metric that we are going to use in order to evaluate our performance is the accuracy basically. And after that, we are just going to go ahead and do the training part. For the training images, we are going to pass the training images. For the validation part, we are going to provide the validation images, and we are only going to train it for the 5 epochs, and let's say what is the kind of output that will be generated. But now, if we just look into this particular layer, we are having the convolution layer, the batch normalization layer, the ReLU activation, the depth-wise convolution, and all the kind of again batch normalization is happening after this depth-wise convolution. Again, the ReLU is activated for that respective depth-wise convolutions. Then again, we are having a layer of convolution, batch normalization, and this is just going on and on until the last particular part where we'll be using the I guess the global average. That was the name. Yes, that's the global average pooling 2D layer. So that's the layer, that was the last layer that we were using from the pre-trained model. And after that we added three different layers, so 128 and 128, two layers of dense or the hidden layers that we have used. And after that, the last one, third dense that we had added, was for the uh, classification layer. So that's the kind of the summary that we have got. And yeah, that's the kind of the whole architecture that we are using. See, all this kind of stuff, how what should be the filters, what should be all the kind of stuff is now getting taken care all the way by this pre-trained models by itself. We don't even have to think about it. That's the power of the transfer learning. And now we can just turn on GPU. You can turn on the GPU. The way to do it is I'll have to go up and click on this arrow, and over here if I just scroll down, yeah, there is the option of GPU, right? I should actually turn it off to have a proper quota for this particular week, or if I just exhaust it. But yes, anyway, you will have to turn on the accelerator and set accelerator, whatever is available you can choose. The one that I personally use is GPU P100. It's always available almost every time. It works like a charm, so you can go ahead and try to use it for yourself as well. But yeah, that's the part that we are using over here for the GPU. And only then your training is going to become very fast, or it's going to take a lot of time, a lot of seconds or minutes, whatever you want to call, in order to train each and every epoch. So for 5 epochs, we are able to see the outputs. And from the first epoch itself, we are getting a really good output, because all the kind of data set that we were having was having only 5,000, I guess, images for the training part, and the validation part was having 1,000 images. So if you could go ahead and augment this data and create some more amount of data set, you would it would take some time to reach this kind of accuracy and this kind of loss. So please go ahead and try it by yourself by augmenting the data. See how is the output getting changed for the 5 epochs. All right. And you are seeing that the end accuracy that we are able to reach is almost 1% over here as well for the validation part. And we'll also look into what is the part, like how is the this kind of thing is working for the test data set. We're also going to look into that. But I hope that the training part is helpful in understanding of how this network is being used in order to train layer by layer all the way up till we get each and every image that we are having is going to pass through this whole architecture, and then it's going to give us at the end in the classification layer that it belongs to which class. This image that we had passed as an input, it belongs to which class. That kind of thing that's happening as usual. And after that, we are using model.evaluate. The model that we had created, it's the same variable that we are using, this particular same model. And then we are using the dot evaluate on the test images. And this verbose equal to 0 basically helps you avoid printing any kind of this kind of output after getting model or after using model.evaluate. So now we have also done this on the test result, and in the test result as well, you can see that the accuracy is just amazing, 99.94%. It's really, really, really great. That's the power of this transfer learning. You don't really have to bother about creating the whole architecture from scratch for this computer vision task. You can directly use it. That's already created by huge companies and already tested on large data sets, and then just borrow some of the layers. Then again, there are multiple ways of using this pre-trained model. At times it will happen you will have to freeze only the feature extraction part of the whole model, and the remaining part you will have to code it by yourself. And all that kind of stuff are there, and we'll be introducing this kind of things in the upcoming projects. But for now, that's that's a pretty much idea about how we are using the basics of transfer learning in order to implement it on our fish data set. So I hope that is clear to everyone. And this is nothing but the loss and the accuracy that we are getting from these results. The first output of the results are containing the loss values, and the second one is containing the accuracy. And then we are just multiplying it to 100 to get 99.94% basically, right? So that's an impressive result that we have got. And again, as I had mentioned, please go ahead and try to augment these images and try to have some more images and see. It will obviously take some more time for training because now you are increasing the data set. But now see, you will be able to see some changes in the accuracy. It won't be really high from the first epoch itself. And now we are going ahead. And we are using model.predict on the test images. And now this predict is just going to give us the output of which out of the 9 classes is having the highest amount of the prediction. And that's highest prediction is what is nothing but as the predicted output basically. That's kind of stuff that we have done over here. And now over here, what we are doing is we are trying to create a prediction data frame. So over here, we are creating the test data frame. Again, we are just creating the copy of it so that we are not actually changing the test data frame that we had created earlier. And then we are having the set that is ready for us. We'll be updating this set on the different labels every time we are going to iterate using this for loop. And now before I go ahead and explain you the idea of this, how this for loop is working, it will be really very good if I'm having the visualization of this prediction data frame. So what I'll do is, because I have not done this particular step, I'll just pause the video over here. I'll just quickly retrain this whole thing because I guess the session was timed out. I did not use the persistence in this particular notebook. But anyway, I'll just retrain this particular thing, and I'll resume the video after that, and I'll show you what are the contents of this spread underscore df. It's really not that difficult to understand, but yeah, just to help you visualize what's going on, I'm just doing this step. So I'll just pause this video. I'll run all, and let's just hope we're getting a good result, and I'll just show you what is the output that we're getting. So guys, I'm back, and I have done a lot of changes over here just in order to have a better visualization for you all. So anyway, I'll just go ahead and explain you all these things step by step. It's just that I should have done this before, but anyway, I've done it right now, and I'll just go ahead and explain it to you. And then I'll explain you how exactly we are able to achieve this kind of thing with the help of this for loop. But in the prediction underscore data frame, we are actually having these 2 columns that was already there in the test underscore df. And the third column that we are adding by ourselves is that the predicted column, that is the pred column. So over here, we are able to compare and see that the results are exactly same for these are the first 10 outputs of the data frame that we are having. And note that I also implemented this reset underscore index and drop equal to true. So what I'm doing over here is, while I did not did this particular step before I paused the video, the idea was that I was getting different indexes over here. It wasn't in an order. So what I did was I just replaced all these unordered indexes into a proper order. That's why I'm using the reset index. And drop equal to true basically means that it was not going to allow this data frame to create an extra column which will be containing the true values of the index. So I'm just dropping them, and that's what I'm saving again in the pred df. And then I'm just displaying the first 10 images, or the path of the images, in the respective outputs of the labels and the predictions. So yeah, that's what we have done over here. And then this is pretty much obvious, why are we getting exactly same labels in the prediction? Because the accuracy of the test data set is 99.94%. So only one or two, I should say only one in this particular case, because it's 99.94%. So only one of the path was not able to clearly, our model was not able to identify if it's the same label or a different label, or the same class or a different class. So I've also done this thing, which was that incorrect prediction. So for that, what I'm doing is, from the prediction data frame, I'm grabbing the values of the rows where the label column was not equal to the prediction column. And we can see that on the 1604 index, we are having this particular thing. And now to visualize this, what was the image, what was the name of the image, I am doing this particular step over here. So this image is actually 293 image, and the true class was a stripped red mullet, and the prediction done by our model was shrimp. So that was an incorrect prediction. That was the only one incorrect prediction, and that's really an amazing output that we are able to achieve in this particular project. And the this particular path is really straightforward thing, but still I'll just go through it very quickly. I've again given a figure size of 15,8. That's something that I always usually try with, and then just play around with this number until and unless I get proper amount of output that my eyes are comfortable to watch. And then I'm just taking out this particular path from the 1604 location, and I'm plotting that with the same. I'm first converting it to numpy arrays and then using IMShow to visualize that numpy array. And then I'm just creating this title with the help of from this path. I'm just splitting this path with the help of this slashes. So the last slash is basically if I just show you what exactly this path contains. I'll also do that for you. I'll also do that for you. What is that path? So in this path, wherever I'm getting this slash, I am just splitting all this. I'm just splitting this whole path with slashes. So every slashes are just going to get removed, and all the things apart from the slashes are going to be a different element of a list. And now the last is basically the name of the image. This is the actual true class of the image, and the predicted class. In order to get the predicted class, I'm again going to access this prediction column of the 1604 row. That's what I'm doing. From the prediction column of this data frame, give me the 1604 row. So that value is shrimp. So that's why the title 3 is going to be shrimp. And that's how we are basically getting the outputs over here. That's what I'm using the f string in the title to get me the the image as the title 2 is the image name, that is the 293rd image. And then comes the title 1, that is the actual label that was given to that particular image. And the title 3 is basically the prediction label. So that's what we are trying to display it over here with red color. The weight of the text is bold and the font size has been set to 15. So I hope this is a good visual of understanding which one was the incorrect prediction basically. And now we can just go ahead and now try to understand what exactly has happened over here. So if you remember, I told you that machines are capable only of reading the and understanding the numbers. So similarly, it's also going to throw an output of a number. So the outputs that we'll be receiving from the model itself will be in some kind of a number. So what we are doing is, again, you can say we are doing some kind of pre-processing over here to convert that numbers into the actual labels or the names of the labels that we had assigned. If you remember, if I just scroll very up over here somewhere, yes, this is the thing where we had got the class indices for the test images. So what we are trying to do is now we are trying to convert this indices into its respective label. That's what we are trying to do with the help of this for loop that we had seen over here. So where is it? Right over here, yes. So for the labels and the values that we were having in that class indices, see, dot item is basically grabbing all this key value pairs in the dictionary, and then we are saying that we are updating this set with the reversed values. Now the value becomes key and the label becomes your value. So now this label is what we'll be able to see in the prediction instead of the numbers. So that's what we are doing over here, a small pre-processing step in order to get this kind of output. And then we are just saying that just create the third column in the prediction data frame, and the third column should have all the values of the prediction. And this prediction is nothing but the the categories 0, 1, 2, 3 all the way up to 8, which class was giving you the maximum probability. That's the value over here. Now, so initially we are having the values, okay, after this particular step. But after this, what we are doing is, on this, where whatever was the values of 0, 1, 2, whatever was the class, we are implementing or applying the lambda function over here and just grabbing the respective labels out of it. So if the class is 0, the respective labels would be assigned in place of 0. So that's what we are doing with the help of this for loop, and then with this two coding lines over here. So I hope this was good enough to understand what exactly or how exactly we got this as the output by using this coding cell over here. And now we have already seen the visualization. Let's go ahead and try to get the accuracy score. We have already got a 99.94, so it's the same thing that we have done over here, 99.94. That's the exact same value, but now we are just again doing it by comparing how many labels are equal to the predictions out of the total data set that we are having, the total number of rows that we are having inside this data set. So we are just doing the same thing. You can completely ignore that part, the accuracy part, but now you can focus onto the confusion matrix. Now see, if you notice, this particular image is pretty much small, so that's where this figure fixes comes into the action. So plt dot figure and fixed size. If you're not comfortable visualizing it, you can just change it. As I mentioned, 15,8 is something that I like to visualize in. So this is again not something that I'm liking. So what I'll do is I'll just try to change it to 8 cross 8 and let's see how is the output. Again, this is not something that I want, and I guess a bit of stretch would be good in the y direction. I guess yeah, this looks pretty much good to me. If you want, again, you can just play around with these numbers. All right. So now, if you can notice, if I just zoom in a bit over here, see these are if you can call this the prediction class. This is your actual class. So all the values that these are basically telling you, like, in the test data set, there were this many images that were predicted as 0, and the actual labels are also 211. If there were any kind of wrong predictions, then we would have got one written on over here. But yes, if you remember, we had one incorrect prediction, and that's the reason that we are seeing this one over here. So that's the, that's the actual reason why we are getting this one, because, the seventh index might belong to that particular class. What was the name? Stripped red mullet, but actually it predicted shrimp. So that's why we are getting a 1 over here. Actually, it was 7, but our model predicted it as 6. So if I just go ahead and show you what is the, what is the 6 and 7 labels that we are having. It was, yeah, over here. So yes, 6 is shrimp, and the 7 one is the stripped red mullet. So that's exactly what we are seeing over here. If I just go ahead over here. So yeah, 6 is something, and 7 is something that we are looking into, and 6 and 7 are the labels which corresponded to these values or the names of the labels. So yeah, that's pretty much about the confusion matrix. You must have seen this in all the other different projects. So I'm not going to explain much more about it, but I hope you got the idea. And then we are just generating the classification report, and I'll just zoom in a bit. So over here, if you can see, all the values of the precision recall and F1 for all the classes are 1. Just note that this is the rounded off value. So 99.94, basically, all the values are getting rounded off to 1. All right, but yes, it's not exactly 1 because of, one incorrect prediction. But yeah, the round off will become 1, and that's why we are able to see all the 1 values over here. Now, the reason I wanted to show you the classification report over here was that if you are having a balanced data set, you will have a good precision recall and F1 score. You always use the classification report, or, basically the matrix of precision recall and F1 only when you are not having the balanced data set. Like if you had looked into the previous projects, in a lot of projects we were not having a balanced data set, and therefore the precision and recall were not really satisfying. But over here, because the overall accuracy score was 1, and we are having a balanced data set, so the data set itself was really good. It was already balanced. If it was not balanced, you can have, you can use some kind of augmentation techniques in order to create extra images from it, or maybe if some of the classes are having extra images, you can reduce it. You can do all that kind of stuff, or some, inbuilt methods through which you can try to balance your data set, and then you can move ahead and you will be able to see this kind of the classification report. But yes, you don't really need to see the classification report if you are having basically the balanced data set. That's what really I wanted to demonstrate, and that's the reason you are getting, pretty much 100% result over here. So yes, we have achieved an 100% accuracy, and this is obviously clearly demonstrating the power of the transfer learning in terms of how easily we were able to implement it, as I've been, explaining about it while explaining the project. So that's the power of transfer learning without using a lot of hassle. We are just using, changing the last few layers, or adding the last few layers, or you can say in terms of machine learning, adding top few layers, and changing the classification layer. But yes, that's the end of this particular project. And over here, we are leaving some of the references for you to try. And the first two links are basically referring to the more knowledge on the transfer learning. In order to, get more comfortable with the transfer learning, you can use the first two links. And the third link is nothing but the implementation part of the transfer learning, where in this particular project, we had done the multi-class classification. Over here, this is only a binary classification, so you can surely give it a try with the similar ideas of what we have done over here. And now moving on to my personal favorite segment of this whole project, that is, you're going to get a chance of earning a certificate if you're going to complete the task that we are having over here for you. So the first task that you're going to have is implementing the same problem using a different pre-trained model. So you can just click on this particular link, it will redirect you to the page. And now you can choose any model that is available over here. So the one that we used was the mobile net v2, this particular one. Let's say now you're going to go ahead and try to use efficient net, or let's say exception vgg 19 16, or let's say restnet, whatever comes to your mind. You just take one and try to look into, like, what are the kind of input dimensions does it accept in this model, and then you just shift that respective coding cell given to you in this particular project, and then see how the output is changing, and try to compare it with the result that we have got it right now. And for a self exercise, what you can also do is you can also create your own CNN model from scratch, and then you'll be able to see the actual power of this transfer learning. Because as I mentioned throughout this project, like while doing everything from scratch, it takes a lot of time in order to think about, like, how many layers are we going to use, how many max pooling layers are we going to use. Then also, like, when we are talking about the like the filters that are present into the convolution layers, how many of them to use, and what should be the strides or the padding and all that kind of stuff. You will just try to, like, you will have to do it by trial and error, and then you will be able to reach to some some kind of an conclusion, or the output of the model which is closer to this. It will be really time consuming. So for sure you can go ahead and try to create your own CNN from scratch and share your, like, ideas in your notebook, how it worked for you. But yes, the one thing that you need to do is you need to implement the same problem statement with at least one of this other state of the art models that we had seen over here. And yes, it's your choice. If you want to again include your own CNN model, you can obviously go ahead and do that. But now coming on to the next task, that is, you're going to try to implement the image augmentation as I had mentioned. Because the training set is only containing about 5,000 images, so we'll try to augment that data and try to expand that data from 5,000. Let's say you're going to take it to 2,000, or maybe at least 1,000 to start with, right? And then you also change a number of other things, like change the number of epochs, then the dense layers that we had used after the pre-trained model, like the top layers that we had changed, we had used two dense layers and then the classification layer. So then you can try to use, maybe let's say one dense layer, or maybe three dense layers, four dense layers, whatever comes to your mind. You can just try it, and also change the number of neurons in this dense layers, apart from the obviously the classification dense layer that we are adding, that must have nine neurons, else the output won't, you will not be getting in proper output. So that's one thing that you need to keep in mind. You try to first of all augment the images for the training part, and then just try out this different epochs, dance layers, and the neurons of that dance layers, and then compare your result with what we are having over here. So these are the main two tasks for you. This is completely optional. If you want to do it, you do it, else it's completely fine. It's just for you to realize, like, how powerful the transfer learning is. So that's about, like, only once you are done with both the tasks, you can click on this form, and it will redirect you to this particular place where you can upload your solution file. So once you are done creating your own solutions, so you can keep on adding your answers, or you can create your own notebook. It's completely fine, but you should have done both of the tasks somewhere in this kind of notebooks. And once this kind of notebooks are ready, you can click on this particular form and come over here and upload this file using this particular option. But now it's really important for you to first of all create an account on our website if you haven't already done that. So I'll just click on this particular Spartificial where it's written in the form, and then in this particular website I'll come over here and click on sign up. And I can go ahead and I can either try to manually sign up, or you can use your Google account, and then you can just in just one step you will be able to sign up on this official website of Spartificial. But because we have already landed on this particular website, let me just go ahead and tell you about some of our programs and the workshops that we offer. So in the training programs over here, we are offering a course on the fundamentals of astrodynamics in Python. So this is the first in its kind that we are launching in India. Before us, no one has launched how we can use Python in order to get the fundamentals of astrodynamics. So that's really something interesting, that if you're interested into astrodynamics or how we can use Python on astrodynamics, you can surely go ahead and try to, like, search more about this program by clicking over here. And similarly, if you are now interested about implementing more of data science in the astronomical aspect, then obviously you can go ahead and check this particular training program. And apart from that, we are also offering a lot of workshops. These are the upcoming workshops. The first two are basically the same. One is for the March batch and one is for the May batch. And over here we are going to and this is basically a 14 days workshop with 7 sessions. And here we are going to focus on how we can solve different kind of problems for space science with Python. And the second that is going to be containing only 2 days of 4 different sessions. And over here we'll be thinking about how you can implement the ideas of the data visualization for the astronomical research. So that's the kind of workshops that we provide. And also apart from that, we also provide guided projects. Obviously this link is available with you, the spartificial.com. You can come over here and explore our website and all the kind of interesting thing that we are offering. But coming back to our form, you will need a project ID and the project name. So as usual, you can go to the top of this notebook, and over here you will be able to find the project ID and the project name. Even in the start of the this particular video, I had mentioned that we'll be using it for filling up the form. So that's what you'll be needing. You just copy this ID and the name and paste it respectively over here. Then give your full name, your email ID on which we'll be giving you the certificate if you're completing the task that we are giving to you. So once you will be submitting this particular form, we'll be going through what you have done. And if you have completed the task, we are not going to look into your efficiency, how efficiently you are coding it. We are just going to see how are you coding it in a way that you're completing the task. That's it. If you have completed the task, you will be surely getting the certificate based on the skills that you have earned doing that particular work. Now it will be based on the hard work that you are putting into understanding what I have just explained in this project, and then using your own ideas to create the different things that I had mentioned in the task, right? So all this kind of stuff will contribute towards adding to the skills of what you have learned in this project, and you will be getting the certificate for the same. And then just before clicking on the submit, if you have yet not subscribed to our YouTube channel, if you think that our content is helping you in some way in improving your skills in data science or in any way, because this is not the only one thing that we are doing. So if I just click on the playlist, you will be able to see all the kind of different playlist. We are also launching the space news. Then we are having this academic projects, obviously. Apart from that, we are also providing the YouTube shorts and the decoded series where we talk about any kind of a topic, and then we try to decode the secrets about that particular topic. So all this kind of stuff we are doing. So if you are getting benefited from this task that we are doing, and if you find it useful, please go ahead and consider this subscribing our YouTube channel. And if this particular video has helped you in any way, do give us a like, and also share it ahead with your friends. And in case of any kind of doubts, you can always let us know in the comments, and we'll get back to you as soon as we can. So with that being said, I'll see you again with some another interesting project like this, and until then, stay tuned. Indiscriminate harvesting, pollution of water bodies, and the accumulation of pollutants have increased the mortality rates among fish species, resulting in a steady population decline. As a result, it is critical to safeguard them. Unfortunately, manual efforts to conserve aquatic species are time consuming and costly. It makes sense to automate the process by leveraging latest technology and human minds together to drive efforts towards a good cause. This can enable ecologists to spend their valuable time from analyzing the amount to addressing the cause. Such models can create a gigantic difference in the long run.